This is Dr. Shankaraiah from Department of Physics. In today's presentation, I am going to discuss question bank on Module 5, Nanotechnology, Part B, long answer questions. So the first question is, what are the two principal factors that cause the properties of nanomaterials to differ significantly from bulk materials? Explain them in detail. So we need to discuss these two principal factors that cause the properties of nanomaterials different from other materials, bulk materials. Okay. So the two important properties that make nanoparticles different from bulk materials are surface to volume ratio, surface area to volume ratio, and quantum confinement effect. So these are the two properties because of which the properties of nanomaterials are different from the bulk materials. So how do they affect the properties of these materials? So the first one is surface area to volume ratio. Okay. So nanomaterials have relatively larger surface when compared to the same volume or mass of the material produced in larger form. So we are saying that whenever you produce nanomaterial, the surface area of these nanomaterials is more larger compared to the bulk material of the same volume or mass of the material in the bulk form. Okay. So how to look into this with an example, I am going to consider a sphere of radius r. Okay. If I take a sphere of radius r, the volume of the sphere is 4 by 3 pi r cube. Okay, so the volume is given here 4 by 3 pi r cube, and a surface area is 4 pi r square, right? Surface area is 4 pi r square. So surface to volume ratio is 4 pi r square divided by 4 by 3 pi r cube, so it is 3 by r. Okay, and for a cube, if you take a cube, the surface area of a cube is 6a square and volume of a cube is a cube. Okay, so surface area to volume ratio is 6a square by a cube, which is 6 by a. Okay. So now as you reduce the size, so now I have a sphere of radius r. If I reduce the size of this spherical particle to r by 3, for example, if I reduce the particle radius to r by 3, then what I'll get is 9 by r. Okay, so the surface volume will increase 3 times to the surface area of this sphere, which is spherical particle which has radius r. When the radius of this spherical particle is reduced to r by 3, then I am going to get the surface area to volume ratio, which is 3 into 3 by r. Okay, so 3 times more compared to the spherical particle of size r. Okay, so when we change the particle size, we have seen that the surface area to volume ratio will increase. Okay, so when the surface area to volume ratio increases, some of the materials which are not catalytic will become catalytic when the surface area to volume ratio increases. Okay, so we will see that. Okay, so as RA decreases, surface area to volume ratio increases. So the properties of materials will be changed. So when we decrease the size of this spherical particle, for example, when we decrease the size to smaller size, then the surface area to volume ratio increases and the properties of the materials will change. The material has high surface energy if it is small in size or vice versa. So if if it is in small size, then the material has high surface energy. Okay. So as the surface area to volume ratio increases, the materials possess good catalytic properties. So material which are inert at the bulk size, they will become catalytic when they reduce to its nano size. Okay, so that is what. So the properties of the materials change when we go from bulk to nano. So thus nanoparticles show enhanced stability and broader scope of applications. In some cases, materials that are inert in their larger form are reactive when produced in the nanoscale form. Some materials which are inert, they will become reactive. Which are not catalytic will become catalytic. Okay, so this affects the strength or electrical properties. For example, a particle of size 30 nanometers has 5% of its atom on its surface area. 10 nanometers has 20% of its atom on its surface, whereas 3 nanometers has 50% of its atom on its surface. So as the size of the particle decreases, the surface area increases, and we can place more particles on its surface. So surface area to volume ratio is very important factor that changes the properties of these nanomaterials. The second one is quantum confinement. When atoms are isolated, the energy levels are discrete. If you know the particle in a one-dimensional box, where a particle is trapped in a one-dimensional potential well with the potential zero inside and the potential is infinite at the boundary at the walls, then if you look at the properties, if you look at the energy levels of this particle that is trapped in an infinite potential, you will find these energy levels are discrete, which is given by n square h square by 8m a square, where a is length of this box. Okay, so when atoms are isolated, when particles are isolated or trapped, we find that the energy levels are discrete, and the discrete energy levels of a particle trapped in a one-dimensional potential well is an example, and this is given here clearly. So this is the potential, that is particle trapped in this potential well, and these are the wave functions are at different energy levels, and is equal to 1, 2, 3, 4, and these are the energy levels at different n. Okay, so different masses, you will have different energy levels because m is in denominator, right? So as m increases, the energy levels will also decrease as they will become closer and closer. Okay, so what happens when we take the many number of atoms together? When large number of atoms are closely packed to form a solid, energy levels split and form bands. Okay, so when you have single particle that is trapped, you will see the energy levels are discrete, but when you have large number of particle atoms are together, then you are going to see that there is going to be energy level splitting and there is a formation of band. Here I have just taken two hydrogen atoms, which is having two, these are the two, hydrogen atom 1, hydrogen atom 2, they have two energy levels, say identical energy levels, and when I bring these two hydrogen atom together, these two hydrogen atom energy levels now split into 4 energy levels because there is a formation of hydrogen molecule. If you take 3 hydrogen atoms, there will be more splitting of energy levels and they will become 6. So this is how the wave function overlap. You will have a molecule formation of molecular orbitals. Okay, so yeah, so this, because of this formation of molecular orbitals, you can have psi plus and psi minus two ways. These are two orbitals, hydrogen atom A, hydrogen atom B. When these two hydrogen atoms together, these wave functions overlap in two ways, and because of these overlapping, you are going to get energy levels splitting. 2 energy levels are going to become 4 energy levels. When you have more and more hydrogen atoms together, you are going to see this the energy level splitting gives rise to the energy formation of energy bands. So nanomaterials represent intermediate state when the dimensions of the box or potential wells is in which a particle is trapped or confined are of the order of the de Broglie length of electrons. If you are taking the particle that is trapped in a box and the size of this so the dimensions of this potential well is of the order of de Broglie wavelength, lambda is equal to h by mv, then the energy levels of electrons will change, and this effect is called as quantum confinement effect. When the material is sufficiently small in size, typically 10 nanometers or less, organization of energy levels into which electrons can climb or fall change. Specifically, the phenomenon results from electrons and holes being squeezed into dimension that approaches a critical quantum measurement called excited Bohr radius. Okay, yeah. So in small nanocrystals or clusters or grains, the electronic energy levels are not continuous as in bulk, but are discrete. So as what we expect is that when we are fabricating and manufacturing these nanomaterials, nanocrystals, where we have many number of atoms, we may expect the formation of bands, right? But we find that the energy levels are discrete. So because of the confinement of the electronic wave function to the physical dimension of the particles. So that is what. So when we are confining the particle in a box whose size is matching with the wavelength, de Broglie wavelength of that particle. So in that case, then we are going to find the energy levels of this nanocrystal, which is having many atoms, still are discrete, not continuous. So these can affect the optical, electrical and magnetic behavior of materials, particularly as the structure or particle size approaches the smaller end of the nano scale. Examples: opaque substances become transparent, inert materials become catalytic, stable materials become combustible, solids turn into liquids at room temperature, and insulators become conductors. So quantum confinement can give rise to quantum confinement can give rise to these kind of changes in properties similar to the surface to volume ratio. So these are the two important factors that affect the properties of the nanomaterials compared to the bulk materials. Discuss in detail how the optical, physical and chemical properties of nanomaterials vary with particle size. So how the properties of this nanomaterial changes with size. Okay. For example, physical properties decrease in melting point with size. As you reduce the size of this nanoparticle, the melting point will also decrease. Chemical properties, as the size is reduced, this material will become better catalytic efficiency through higher surface to volume ratio. Electrical properties, for example, increased electrical conductivity in ceramics and magnetic nano components, increased electric resistance in metal as the size is reduced, increased magnetic coercivity up to a critical grain size, superparamagnetic behavior. Mechanical properties, improved hardness and toughness of metals and alloys, ductility and superplasticity of ceramic. Optical properties, spectral shifts of optical absorption and fluorescence, increased quantum efficiency of semiconductor crystals. Biological properties, increased permeability through biological barrier, for example, membranes or blood-brain barrier, etc. So there are many changes in the different properties, for example, physical, chemical, electrical, magnetic, mechanical, optical and biological properties of these nanomaterials when the size of the particle decreases in size. Describe the role of surface to volume ratio and quantum confinement on electrical, magnetic and mechanical properties of nano-sized material. So we have discussed just now the surface area to volume ratio and how the properties of the material become. Some of the materials which are inert will become reactive, and which are not catalytic will become catalytic, and this these reactive and inert, when the materials in bulk size they are inert, but now when we reduce the size, when we go to the nano size, they will become reactive. So these will change the electrical properties of the material. So surface area to volume ratio will definitely affect the electrical properties and mechanical properties of the material. Similarly, quantum confinement can make many changes, as we discussed. Opaque substances will become transparent, and solids become liquid, stable materials become combustible, inert materials will become catalyst, insulators will become conductors. Okay, so quantum confinement and surface area to volume ratio change many properties of the material, like electrical, magnetic and mechanical properties here. Discuss with a neat sketch how the nanoparticles are prepared employing the bottom-up method, namely sol gel. So how do we prepare nanoparticles using sol gel method? Sol gel method involves the formation of a colloidal suspension and gelation of the solution to form nanopowders in a continuous liquid phase gel. Okay, first we need to form a colloidal suspension, and then when we wait for some time, there will be aging, and during this aging time the solution will get gelated and there will be a formation of gel. Gel is nothing but a polymer network, and then this gel can be used to form nanopowders. So what is a colloid? A colloid is a mixture in which an insoluble substance of particles are suspended throughout another substance. So one will solute and solvent. So initially a homogeneous solution of a material is prepared and is used as a precursor for nano fabrication. The solution is deposited on a suitable substrate. You can deposit this solution onto a substrate by spraying, dipping or by spinning. So it is kept for a while for gelation. This is called aging time or gelation time. So during this gelation time, the material gradually loses its fluidity and undergoes a transition from viscous liquid to elastic solid state, and this time depends on the viscosity and temperature of the solutions. So this is the schematic of sol gel method, where you prepare a precursor, and then once you have this solution, which is a colloid, you can directly wait for some time. It will get gelated, and then this gel can be used. So you can heat this to supercritical drying of this gel can give you polymer networks, or sintering of this network will give you dense ceramic material. So we can directly from the solution we can draw this coated substrate. Once we can coat this solution onto a substrate by coating, spinning or coating, we can prepare dense thin film, or we can use this solution to draw fibers, or we can dry this solution to get powders. So we can form different kinds of nanomaterials using this solution by critical drying or supercritical drying of this solution. So basically the steps involved in the solution sol-gel method for nanoparticles formation are given here. So the desired colloidal particles are dispersed in a liquid to form a solution. First we need to dissolve the colloidal particles in a solution, and then the deposition of the solution on the substrate by spraying, dipping or spinning. Once we get the solution, we are going to deposit this solution on a substrate for various techniques like spraying, dipping or spinning. The particles in the solution are polymerized through the removal of the stabilizing components and produces gel. This is called condensation. So once we pour this solution on a substrate, after the aging time or gelation time, we will find that the solution get polymerized, and the final e-treatment of the solution can remove all the unwanted organic inorganic components and form an amorphous or crystalline nanomaterials coating on the substrate. So the main benefits of this sol-gel process are the high purity and uniform nanostructures achievable at low temperatures. It is normally used to produce metal oxide nanomaterials. How nanostructured materials are synthesized from the gas phase by process of chemical vapor deposition. Also draw a schematic of typical chemical vapor deposition reactor. Chemical vapor deposition is a widely used method for depositing thin films for a large variety of materials, range from fabrication of microelectronic devices to the deposition of protective coatings. So we use this chemical vapor deposition techniques in different fields. In a typical chemical vapor deposition process, reactant gases at room temperature enter the reaction chamber. First, these reactant gases are going to enter into the chamber where reaction will take place. The gas mixture is heated as it approaches the deposition surface, heated radiatively or placed upon a heated substrate. So depending on the process and operation conditions, the reactant gases may undergo homogeneous chemical reactions in the vapor phase before striking the surface. So in this method, the material is heated to gaseous phase and allowed to condense on a solid surface in vacuum. Nanomaterials of metallic oxides or metallic carbides can be formed by heating metal and carbon or metal and oxygen in a vacuum chamber to gaseous phase and allowed to deposit on the surface of a solid. Pure metal powders are formed by this method. The metal is melted, excited with microwave frequency and vaporized to produce plasma at 1500 degrees centigrade. By cooling this plasma with water in a reaction column, nanoparticles are produced. So the grain size of nanoparticles depends on concentration of the metal vapor and its rate of flow in the reaction column and temperature. So this method can also be used to grow surfaces. There are a great variety of chemical vapor deposition processes such as atmospheric pressure chemical vapor deposition, plasma assisted chemical vapor deposition, low pressure chemical vapor deposition, photochemical chemical vapor deposition, laser chemical vapor deposition, chemical beam epitaxy, and chemical vapor infiltration. So these are some of the process, different variety of process in chemical vapor deposition techniques, and the schematic of this chemical vapor deposition technique is given here. So you have reactant gases entering the chamber, and that is heated to produce a gas. That metal will be deposited onto a substrate, and you are going to produce nanoparticles. What is the principle behind TEM? Explain transmission electron microscopy characterization technique to analyze nanoparticles with neat diagram. So TEM or transmission electron microscope, in this transmission electron microscope, electrons are accelerated from 10 kilovolts to 1 mega electron volts, projected onto a thin specimen with thickness less than 200 nanometers. The electron beam is projected onto the specimen by means of condenser lens system and penetrates the sample thickness either deflected or indeflected. Okay. So the advantages of TEM are highest magnification of the order of micron and its ability to provide both image and diffraction information from a single sample. So there are two scattering processes experienced by the electrons during their passage through the specimen. So the elastic scattering involves no energy loss and gives rise to the diffraction pattern. Inelastic scattering interactions between primary electrons and secondary electrons at heterogeneities such as grain boundaries, dislocations, defects, density variations in the intensity of transmitted electrons. So the high magnification of resolution of transmission electron microscope is a result of the small effective electron wavelength, which is given by this de Broglie wavelength relation. Lambda is equal to h by square root 2 MeV, where V is the potential. So the higher the operating voltage of a TEM, greater is the lateral spatial dimension, and the disadvantage of this TEM is its limited depth resolution. So you can use selected area diffraction, which can be used to look at the crystal structure of different samples and to look at the Bravais lattices and lattice parameters using this selected area diffraction. TEM can be used to determine the melting point of nanocrystals, and electron beam is used to heat up the nanocrystals, and melting points are decided by the disappearance of diffraction pattern. So TEM can be used to measure mechanical, electrical, and individual properties of individual nanowires and nanotubes. So this transmission electron microscopy schematic is given here. So the basic it gives us the following information. Morphology, you can get the morphology information from transmission electron microscope, which will tell you about the size, shape, and arrangement of particles, as well as their relationship to one another on the scale of atomic diameters. We can also get the crystallographic information, the arrangement of atoms in the specimen, and the degree of order, detection of atomic scale defects for few nanometers. And compositional information also we can get. The elements and compounds of the sample is composed and the relative ratios. So transmission electron microscope can tell us about the morphology of the material, crystallographic information of the material, and the compositional information as mentioned here. Okay. So explain the characterization of nanoparticles by using X-ray diffraction analysis, which gives the information about particle size and composition. Most of the metals and alloys are crystalline in nature. So hence one of the most useful characterization technique is X-ray diffraction. X-ray diffraction will tell us about the nature of the material, whether it is in crystalline shape or amorphous phase. So XRD or X-ray diffraction is basically based on Bragg's law, which is 2D sin theta is equal to n lambda. So the intensity of diffracted X-rays is measured as a function of diffracted angle and the specimen orientation. So this diffracted pattern is to identify the specimen's crystalline phases and measure the structural properties. So we can use this diffraction pattern to look at the crystalline phases of the material, as well as its structural properties also we can study. So the diffraction peaks are accurately measured with XRD, which gives information about homogeneous and non-homogeneous strains. If there is no inhomogeneous strains present in the material, the crystallized size can also be estimated with the Scherer's formula. D is equal to K lambda by B cos theta B, where B is the full width of maximum and theta B is the angle of diffraction, and K is Scherer's constant and lambda is the wavelength. So using this X-ray diffraction, we can look at the crystalline size as well as the particle size, okay, composition. Analyze the applications of nanotechnology in various fields such as bio, medical, electronic, and industry. So nanotechnology has a wide range of applications. Starting from medicine, you can use these nanomaterials in drug delivery systems. Chemical industry, you can use the impregnation of papers to get different concentration or different concentration of colors, different colors. You can use this use nanoparticles and adhesives, magnetic fluids. You can also use them in coat paint systems. You can also use in engineering, wear protection for tools and machines, scratch resistant plastics, electronic industry, data memory, displays, laser diodes, glass fibers, optical switches. So you have so many applications in electronic industry. Construction also, we can use these nanoparticles as construction materials, thermal insulation, groove motor, packet coatings. Automotive industry, we can use them in automotive industries as catalyst, sensors, textile fabric, nano ovens, surface process textiles, smart clothes, energy as fuel cell, solar cell batteries, capacitors. We can use nanomaterials as in energy, also in cosmetics, food and drinks, household, sports and outdoors. So there are many applications as mentioned: bio, medical, electronic, and industry. Okay, so that is what we have discussed. With a neat sketch, explain ball milling process for synthesis of nanoparticles, list advantages and disadvantages. In ball milling method, which is also called as mechanical crushing, small stainless steel balls are made to rotate inside a drum. So this is the drum. So you have this drum, and these are all the stainless steel balls. So these balls are, once we switch on the power, this drum will rotate, and hence these balls will also rotate and drop under the influence of gravity onto a solid present in the drum. The solid is broken into nanocrystalline. So you have a solid material, for example, here, and you have all these stainless balls. As you rotate this drum, these balls will come and fall onto this material, and this material will be broken into small nanocrystallites. Ball milling can be used to prepare a wide range of elemental and oxide powders. For example, iron with grain size of around 10 to 30 nanometers can be formed using this ball milling method. A variety of inert metallic compounds based on nickel and aluminum can also be formed. Ball milling is preferred method for preparing metal oxides. So to prepare metal oxides, we can use this ball milling method, where we can obtain nanoparticle or grain size around 10 to 30 nanometers. So advantages of ball milling method, it can produce very fine powder. You can use for both wet and dry grinding. Toxic substances can be grounded as cylinder is closed system, whatever drum we are saying. And disadvantages are very noisy machine, high energy consumption, potential for contamination of these materials which we are going to prepare in this ball milling method. Okay. So describe various techniques of physical vapor deposition. So physical vapor deposition involves conversion of solid material into gaseous phase by physical process, which is then cooled and redeposited onto a substrate as per the requirement. Okay. So in physical vapor deposition, basically first we are going to take a solid material, and then we are going to heat this solid material where the solid will convert into gas, and then we are going to deposit these gas particles onto a substrate to form this material. Okay. So all the reactive physical vapor depositions or process combined have the following steps. First, a method for depositing the metal, combination with an active gas such as nitrogen, oxygen or methane, plasma bombardment of the substrate to ensure a dense hard coating. First, we are going to add active gases to the metal, and then we are going to use the plasma bombardment of the substrate to ensure dense coating of this metal onto the substrate. So PVD differs in the means of producing for the metal vapor and details of plasma creation. The primary physical vapor deposition methods are ion plating, ion implantation, iron plating and ion implantation, sputtering and laser surface alloy. So these are some of the methods of physical vapor deposition technique, and this is the schematic of physical vapor deposition technique, where plasma is bombarded. Bombardment of plasma will give rise to this dense coating of these metal particles in gaseous forms onto a substrate. Thermal evaporation is one of the simplest and most popular synthesis methods, and it has been used very successfully and versatile in fabricating nano belts and nano wires with various characteristics. Multi-wall and single-wall carbon nanotubes have been successfully fabricated in this system using hydrogen and methane reactants. Metal catalysts such as gold, tin, copper have also been used to achieve size control alignment. Okay, so this is the physical vapor deposition technique, and different variety of techniques are there. Methods are there in physical vapor deposition: iron plating, ion implantation, sputtering, and laser surface alloying. And yeah, so this is the schematic of physical vapor deposition technique. So these are some of the textbooks I have used and reference books to look at. And to summarize, I have basically discussed question bank on module 5 nanotechnology on long answer questions on nanotechnology. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.